Okay, hello everyone. This is Ken 422 Chemical Reaction Engineering, um, week 13, and today we'll be talking about heterogeneous reactions, and this is the last two sections from the Levenspiel book, chapters 17 to 26. It's a very extensive topic with a lot of details. However, as one of the last sort of things we're going to discuss in this course, I'm just going to give you a quick overview of heterogeneous reactions and the type of things you deal with when trying to design a heterogeneous reactor or multi-phase reactor, which is quite common in industry. However, it's beyond the scope of this course, and probably you'll learn this through experience, or maybe in a graduate course, or maybe in a sort of a PE preparation course, whichever you choose to do. And the thread between, the transport courses, fluid mechanics, mass transfer, heat transfer, there's a thread between them. And once you start seeing how these phenomena behave in terms of having a driving force over resistance, it becomes more obvious and becomes easier to absorb. So moving on, so today we'll be talking about heterogeneous reactions, and I'll also be talking or presenting a summary of the course, or just picking a few slides which will present the main topics which you need to focus on as you do your preparations for the final exam. Your final exam will be scheduled during the normal schedule, which is listed by the university. I'm gonna look it up and give you the exact date and time, but you have to be there and you have to do it live. So make your preparations from now to free up this time slot to be there and do your test. I won't be able to give any makeup tests or any sort of push the test to another time, because you need to submit the grades and then get all these things done with. Your homework 9 is due today, and again, make sure you submit all your homeworks. I'm giving you until Friday, November 27th to submit all your homeworks, any missing assignments you have. There's actually a few of you who could benefit a lot from just submitting the missing assignments. Your homework is 25% of the course. So, losing 20% from this 25 by not submitting homeworks is probably not the best idea. I'm gonna put out a review problem set, whether tonight or tomorrow morning. And as you've seen from previous tests, this review problem set will guide or should give you an expectation on how your final exam is gonna look like. Okay. I just need time to go over your exams, go over the previous homeworks, and try to pick the most representative problems as we move on. And this problem set will be due by next Friday as well. So, make sure you study and, prepare, etc. All of this nice stuff. Okay. So let's move on to the first slide. And again, today we'll be talking about heterogeneous reactions and providing a course review. Yeah, next week as well, I'm gonna have a problem solving session where I'll go over the problem set, which I'm gonna send you guys. And I'm gonna hold this problem session during the scheduled lecture time from 2 to 4:30. And it will be, live, so feel free to join and ask any questions, or if you have any other questions you want to ask about in terms of the homework, in terms of the final exam, you can ask it then as well. And I'll also record the lecture and post it online. There should not be any issues this time, hopefully, and it should be posted without any problems. What else do I want to tell you? Yeah, your final exam, you should expect your final exam to be along the same sort of arrangement as the previous two exams. You're going to have a chunk of it, about 20%, maybe a bit less this time. Multiple choice problems, or, sort of easy questions at the beginning. And then you're going to have 3 or 4 problems to solve by hand. Probably 4 problems you're going to need to solve by hand. 3 of these problems will be straightforward. 1 will be difficult. So could be on any of the topics we're going to discuss. So as long as you understand the basics, you understand all, you do all your homeworks, you're comfortable with the homeworks, should be able to get, in the 70 range without any issues. Okay. And yeah, so before starting, one more point, I posted all your grades and you have a running total column. And this running total represents how many points you have so far from the 75 possible points you can get. Okay, we had the homework is 25%, your exam 1 and exam 2, both are 25%, so it's 50. 25 plus 50 is 75. You can still push your homework grade if you submit your missing assignments and you submit the remaining assignments. And then the remaining 25 will be from your final exam. And then you can do your calculations to, see which grades, if you can get an A, get a B, you want to pass, you can do your own calculations and make your own sort of arrangements and planning as we move towards the end of the course and the final. Okay, so let's get started. So what's a heterogeneous system, or what's a heterogeneous reaction? Heterogeneous reaction is when you have more than one phase, right? So you have a combination of gas, liquid, and solid. And we touched on this last week when we were talking about, having a bubble column reactor where I bubble some gas in a liquid phase, and I have a reaction, the molecules move from the gas phase to the liquid phase, they react, and then you have a reaction in the liquid phase, or you can have a gas-solid reaction, the gas molecules move to the catalyst surface, react, and then you have some product. And these are typically called the heterogeneous reaction. And we haven't really talked about it before when talking about ideal reactors. So previously, when we were talking about ideal reactors, for a CSTR, you sort of assume that everything is in the liquid phase, right? For a PFR, sort of assume that everything as well is in the liquid phase within the context of our course. And we've touched a bit on having a gas phase reaction, how having a gas phase reaction, now you need to account for, volumetric changes with the number of moles. So if I have A plus B goes to R and all of them are in the gas phase, I have 2 moles coming in, 1 mole coming out, and this is going to affect the volume of your system, or the volumetric flow rate. So you're going to have a change in the volumetric flow rate if it's only a gas phase reaction, as opposite to a liquid phase reaction where really the density does not change. And we touched on this before. However, now we're going to talk about multi-phase systems. And the reason for having multi-phase systems is due to the nature of the system, or the nature of the objective you want to achieve inside this reactor. And typically, a reaction requires the presence of more than one phase to proceed at the rate at which you want it to happen. And this could be for many reasons. For example, if you have 2 gases, you want to react them, and they don't react readily under normal conditions, or it's a very endothermic process, and you cannot add a lot of heat because it's a explosion hazard. So I add a catalyst there, a solid catalyst, and I make them react at a low temperature, and now I have a gas-solid reaction. Alternatively, for bubble column reactors, most of the time it's a highly exothermic process, and I'm using the liquid phase to sort of absorb some of the heat and help maintain the isothermicity of the process. Okay, and in a heterogeneous reaction, the reaction may take place in one phase, more than one phase, or even at the interface between the phases. And I'm not sure if you've touched on this in mass transfer. However, if I have 2 phases in contact with each other, probably touched on this when talking about Henry's law, for example. I have for example, I have gas and liquid. I have an interface between them. I have my gas bulk. I have my, gas liquid interface. I have my gas film, my liquid film, and then I have my liquid bulk, right? And each of these sort of stages has its own resistance to flow, depending on the nature of the species and the operating conditions. Okay, and then there as well in a heterogeneous system. So talking about the 4th point here, does not necessarily have to be a catalytic system. You can have a heterogeneous system which is non-catalytic, and you're just having a reaction without a catalyst. They react readily. Gas and liquid are reacting readily. One thing comes to mind is using MDEA or MEA, an amine for stripping H2S or stripping CO2 from a natural gas feed. This is a chemical reaction, and it happens readily. You don't have a catalyst there. Just introduce the gas and the liquid to each other, and your MEA or amine eats up the CO2. They form a carbamate, which is an intermediate chemical, and eats it up basically from the gas feed. So this is an example of a heterogeneous process, which is non-catalytic. Okay, and catalytic reactions are often heterogeneous. Okay, so most of the time, if you have a catalyst, you're going to have a multi-phase system. Now, at the there are some fancy ideas now floating. Sometimes you might have a liquid catalyst in very unique cases. If you're dealing with, if you end up working with metals and steel making and metal making, they like to use. There's the idea of having an oxide fuel cell, where you have a liquid catalyst or sort of a liquid type of approach. So there are other ideas as well. However, most of the time in your standard typical chemical engineering process industries, you have a catalyst. It's a multi-phase system, and the catalyst is usually separated from the products and recycled back. So if I have a gas liquid system or gas solid system, my solid is the catalyst, my gas are the reactants. So I'm reacting A and B on a catalyst surface, and then I get a product C. If C is in the liquid phase, for example, I then take the liquid product with the catalyst, recycle the catalyst, separate the solid catalyst and recycle it back to the process. And then I have a clean stream of liquid. And ways of separating solid from liquid, there are many ways to do it. You can have a centrifuge, you can have this or that. There's many different technologies, which you'll probably see throughout your career, or as you throughout your continuous education as part of your career. Okay, so some examples of gas solid systems: oxidation of metals. The way you oxide metals is you bubble basically oxygen in a molten, or in this case we're just talking about gas solids. So you can have aluminum. If you polish it, after a while changes color because oxygen is reacting on the metal surface. Burning of coal, very obvious one, or burning of wood even, catalytic formation of ammonia. And if you make ammonia through the Haber process, where I get nitrogen, I get hydrogen, I use a catalyst and to make ammonia. Oxidation of ammonia, roasting of sulfide ores to give metal oxides. So there's a lot of examples. Similarly for gas liquid, making chlorobenzene. Chlorine is in the gas phase, benzene in the liquid phase. React them to make chlorobenzene. Reacting ammonia with liquid sodium to make sodium amide. Again, as we said previously, or as I said on the previous slide, reacting H2S with a methanolamine or an amine in a stripper or an absorber system to basically clean out all this acid gas from your natural gas. Absorption towers, all of these ideas are gas liquid systems. Liquid solids, attack of metals by acids, ion exchange columns. And then you have gas liquid solids, hydrogenation of a liquid using a palladium or carbon catalyst. So, I have a liquid phase, I bubble hydrogen through it, and I have a palladium floating in the liquid, palladium catalyst floating in the liquid phase, and I make hydrogenated liquid. Alternatively, a very common gas liquid solid system is the Fischer-Tropsch process, where I bubble hydrogen and carbon monoxide in a continuum of wax, and this wax has iron catalyst or cobalt catalyst. Hydrogen and carbon monoxide react and they make diesel, and then I separate the diesel from my wax, from my catalyst, and I recycle the catalyst back, take the diesel and sell it to the market. Liquid-liquid reactions are also possible, and these are considered multi-phase reactions because these are liquids of different densities, different miscibilities. They don't readily mix and absorb within each other to form a homogeneous mixture, so they are considered a heterogeneous type of process. So nitration of organics to form nitroglycerin, oxidation of organic to make hydrogen peroxide. These are examples of liquid-liquid reactions. Okay. So continuing this idea of having a catalyst, or most catalytic systems are a multi-phase systems, and I'm sure you've covered this before, but the idea of a catalyst is that introducing a new reaction pathway with a lower energy barrier between the reactants and products, right? So if you have a very high activation energy, which either needs a very high pressure, very high temperature, a very complex sort of design to occur at normal conditions, I can always introduce a catalyst to reduce this activation energy, reduce the barrier, make the reaction easier to happen. And one thing to understand about the catalyst is that it changes the reaction mechanism, right? So I'm not sure if you've taken this in organic chemistry where you draw, the ion jumping from here to here, all this cute stuff to make a final product. When you have a catalyst, it changes this completely. So for example, if I am reacting carbon monoxide and hydrogen, if you draw your typical mechanism, you're gonna see OH dissociate, H plus and H, 2H plus, and then I have a carbon monoxide, maybe one of the ions go here, and then they react, all of the stuff. However, when you have a catalyst, your mechanism now becomes the catalyst is gonna absorb the CO, is gonna split the CO into carbon and oxygen. The oxygen will readily react with H to make OH. The carbon will readily react with hydrogen to make a hydrocarbon, and then the CH chain propagates and grows, and the OH chain takes another hydrogen, makes water, and the CH chain makes a hydrocarbon, right? So completely change the reaction mechanism. And this is the purpose of a catalyst. It's going to change the reaction, or basically make another mechanism which with a lower activation energy and more feasible type of occurrence. And you should all know this. I'm sure you've taken it in all your chemistry courses. And when talking about the reaction rate, so the reaction rate will be faster with a catalyst than without the catalyst. Right? All of these are sort of intuitive. So let's take a simple case or a simple example of a multi-phase system. In this case, it's a gas solid system where I have carbon particle being burned in air. Okay, so I have a carbon particle, or basically a piece of coal. You can think about it. I have oxygen going on the surface, burning this, making CO2. And if I think about the stages of how this reaction happens, or how this reaction proceeds, and the specific details of how this thing occurs. So if you think about it, oxygen has to diffuse and arrive at the surface of the carbon particle. So oxygen molecules from the air, or they have to find their way onto the surface of the carbon particle, and this step does not happen readily, right? It's controlled by diffusion or mass transfer coefficient, and at this stage, you should know what a diffusion coefficient is, what a mass transfer coefficient is. You should understand the idea of diffusion from a mass transfer perspective and from a heat transfer perspective. If you have no idea what diffusion means, go study it. Make sure you don't graduate until you know what diffusion means from a mass or heat transfer perspective. Okay. Once the oxygen finds its way to the surface of the catalyst, the carbon on the surface is going to react with the oxygen to make carbon monoxide. And the rate of this reaction depends on the reaction rate coefficient, right? So now, once the oxygen finds its way in contact with the carbon molecule, they react and you get your product. And this is basically your reaction. You have your reaction rate coefficient, you have your reaction rate, you have all of these typical sort of reaction engineering or chemistry expressions. Then after the reaction happens, or while the reaction happens, let's not jump. Step number 3, the reaction enthalpy is released. So if it's an exothermic reaction, I get some heat being released, and this heat gets released to the environment, or it might get released into the system. In some cases, basically just gets released depending on how you're running this process. And then the final step, your carbon monoxide, your product, has to find its way from the surface of the coal or from the burning surface all the way to the atmosphere, or to the continuum in which this reaction is happening. And again, this step as well is controlled by your diffusion mass transfer coefficient. Okay, so I have 2 mass transfer controlled steps and 1 reaction rate controlled step. First mass transfer control step is oxygen finding its way to the surface of the particle, and then second mass transfer control step is the product CO2 finding its way from the surface of the particle back to the continuum. And the resistance to the mass transfer occurs within the vicinity of the solid particle, and this is called the gas film, where this is really where your diffusion or mass transfer coefficients, mass transfer resistances play a role in controlling this reaction. And some processes are mass transfer limited, some processes are reaction rate limited. So If the rates of mass transfer are much slower than the rate of the reaction, the process is called mass transfer limited. And in multi-phase processes, this is actually quite common, where the design of the reactor now is a function of the mixing pattern, right? The mixing pattern starts playing a more important role than the catalyst or than the nature of the reaction, because I need to find the best mixing profile that's going to minimize my mass transfer resistance so that my overall reaction can proceed faster. And if you think about it, your overall rate of this process is a function of your slowest step. So if my mass transfer or my diffusion coefficient is very slow and takes forever for the gas to reach the surface, then I need to design my reactor so that I overcome this resistance. Designing your reactor so that this happens will not give you a lot of benefit because the reaction happens readily, right? So you need to design to minimize the mass transfer resistance. On the other hand, if the mass transfer occurs very quickly and your reaction is actually extremely slow, then in this case, you need to design your reactor in a way so that the reaction proceeds faster. Maybe you want to have, interstage heating if it's endothermic. Maybe you have a lot of cooling internals if it's exothermic, just to drive this reaction forward, because this is really your rate limiting step in your overall process. So these are just two ideas, and now we're introducing the idea of when you have multi-phase systems, you need to start thinking about mass transfer resistances, and eventually you might start thinking about heat transfer resistances as well, and how that might affect your catalyst or burn your catalyst or other ideas. Okay. So again, this is how your typical diffusion occurs. So if I have a gas or a liquid, gas solid reaction or a liquid solid reaction, my molecule has to diffuse through a bunch of stages, or has to move through a bunch of stages until the reaction happens. So the first stage here is your bulk gas phase. I have good mixing, the concentration is constant, right? So I have my bulk gas phase or my bulk liquid phase. So if we're thinking about the example of oxygen, I'm reacting with carbon or with coal. Oxygen is coming from, let's say, air. And my bulk air phase, we have oxygen 21%, it's there. It's well mixed, the concentration does not change a lot. However, as this oxygen moves closer to the surface of the reaction, I have my boundary layer. And the idea of boundary layer is very common in transport phenomena. You must have heard about it when talking about fluid mechanics, or maybe reading about, in any type of fluid phenomena out there. And the boundary layer really is the area close to the surface of a solid or of a liquid. And this is where a lot of the transport resistances happen. This is where a lot of the flow resistances happen. And the idea is, if you think about it from a mathematical perspective, you're getting closer to your boundary condition. So you have to give it extra attention, because your solution near boundary condition is always more transient than your solution far away from your boundary condition, right? And this transient nature near the boundary condition requires attention, and this is really where you need to put in a lot of care. So in a boundary layer, your liquid usually, or your molecule slows down by a lot, right? And your fluid is much slower. So if you remember your flow profiles, if you have a pipe, it's sort of like, it's curved, right? And the velocity near the surface is much lower. And this very low velocity results in a drop in concentration of your gas phase. So once it gets through the boundary layer, I hit the surface, or hit the surface of the solid, and I have two concentrations. This is a concentration of my oxygen on the surface of the solid, and this diffusion here depends on your diffusion coefficient, your Henry's law, your mass transfer coefficient. How fast will this, or how effective will this molecule get absorbed into the solid? Okay. And once it reaches the solid, the reaction could happen at the surface, or sometimes if you have a catalyst that's porous means it's like a sponge, then maybe the gas needs to dance around inside the sponge until it finds the site for the reaction. And the reaction will happen either at the surface, if it's a surface reaction, or throughout the solid if the solid is porous, right? And most of the time, the reaction will happen readily. So once your molecule gets here or gets inside the solid, it will react instantaneously to make your product. Okay, and this is how it goes. You have a bunch of resistances. And when you think about mass transfer resistances, your mass transfer resistance, typical to any transport resistance, is a function of your driving force, which is your concentration, divided by your length scale, which is the distance, right? So mass transfer, you typically see partial n by partial x, partial c by partial x. You know, conversely, in heat transfer, it's what? It's partial t by partial x. You know, in fluid flow, it's usually partial u by partial x. Sometimes, if you're talking about a complex fluid, it could be maybe partial p by partial x. But you always have a driving force divided by a length scale, and this defines your resistance, right? If this delta x is very big, then my overall ratio will be low, right? My partial c by, or delta c by delta x will be low if my delta x is very large. Conversely, if your delta c is very low, so I have the concentration gradient is not sufficient to drive this mass transfer, you're going to have poor mass transfer, which is going to limit your reaction. Some ways to avoid this, or some ways to either basically make this delta x much lower. So if I make the delta x much lower, my partial c by partial x becomes much larger, and the reaction, or the mass transfer element of this reaction gets pushed up, or happens much faster, is by having mixing, or by operating in a turbulent regime, or controlling these elements. If you have a gas liquid flow, maybe making the bubble size much smaller so that your surface area to volume ratio is much higher. If you have if you're running in a CSTR, you had maybe an impeller which mixes the system very well, and you don't have a lot of dead zones, as we talked about last time. And these will help to reduce the mass transfer resistances in your process. Okay, and these are some reactions, or this is the reaction if you want to derive it. So if I assume that the reaction is first order in the fluid, and we're talking steady state, unsteady state is a completely different game. But if you assume it's in steady state, and you want to have a look here at the equation, so I have 1 over v dNA by dt. This is the typical, reaction rate based on unit volume. We've talked about this week 1, very long time ago. And now it's equal to minus d AV dCA by dt, by dx, sorry. And you can see now that it's not only a function of your concentration gradient. However, I also have a coefficient here, or a slope here. This is called my diffusion coefficient, and AV is called the surface area per unit volume, right? And this is surface area per unit volume variable, let's call it the variable, is one of the very important variables, and actually one of the more difficult variables to measure and quantify for any process. And the diffusion coefficient you can typically calculate readily. I'm not sure if you've covered it, but there are a bunch of equations. There's Chapman-Enskog. There's maybe Einstein equation also as well. You can calculate your diffusion coefficient if you know it's if you know your two chemicals in the game. You can calculate your diffusion coefficient just from their densities, molecular rates, all of this stuff. And if I sort of expand this equation, so if I write minus dAV, and then instead of dCA by dx, I just write Ca in the liquid minus Ca on the surface. So this is my bulk concentration. This is my concentration at the surface. If I go back, have a look, Ca is the bulk concentration. This is the concentration at the surface, divided by delta x. And then if I divide my diffusion coefficient by delta x, I get my mass transfer coefficient, okay? And your mass transfer coefficient, which is the KL, you can usually get it from correlations. Alternatively, and very commonly in more complex processes, you'll find correlations for KLA directly. So instead of finding a correlation for KL and finding a correlation for A and multiplying it, and this way you're multiplying errors, because a lot of these correlations are empirical based on experiments. So you don't want to multiply two equations based on experiments. This way you're basically multiplying their errors as well. So in more complex processes, you'll find correlations for KLA, and you can calculate your KLA directly. And again, your diffusion coefficient has units of meters squared per second. You need to know this. Your KL by itself has units of meter per second, right? Because KL is equal to your diffusion coefficient divided by delta X, and this will be meters squared per second divided by meters. It will be meter per second. Your surface area per unit volume always has units of length minus 1, or meters squared per meter cubed. This is how it's usually described. And one thing to know or to remember about surface area per unit volume is that a smaller bubble will have a higher surface area per unit volume than a larger bubble. A smaller catalyst particle will have a higher surface area per unit volume than a larger catalyst particle, right? That's why you want to keep your catalyst as fine as possible and find the balance between having a very fine catalyst and your pressure drop. Because your fine catalyst will have much higher surface area per unit volume, so you have a lot more surface area available for the reaction to happen. You have a lot more active sites available for the reaction to happen, and this way you can possibly have your reaction run in a more effective way. Similarly for the alternative form of this is just writing it this way, making a simplification where I just write it as minus KRAV multiplied by CAS. And here we're getting close to the idea of having Henry's law and just having it as a function of the concentration at the surface. So you can write them in both ways, where I can have my mass transfer coefficient, KLA, as a function of my driving force, or alternatively, I could have a reaction rate coefficient as a function of CAS. Okay. And these two equations occur in your process. So the first equation, where I have my mass transfer coefficient, represents the trip of your molecule from the bulk phase all the way to the surface. And then the second equation here represents the reaction of the molecule on the surface, right? So your overall process is actually a combination of these two reactions, right? This is your mass transfer. This represents your mass transfer balance, and this represents your reaction balance. Again, this is your reaction rate coefficient, and AV is basically KRAV has units of 1/2. This is your reaction rate constant, which we typically talk about. And if you remember, we don't represent it as AV. We just have K CA to the power 1 or CA to the power 2, whatever. So because it's hard to quantify this surface area to volume ratio unless you really know the specifics of the catalyst or you have more details. But for most calculations, or for most derivations for multi-phase systems, these are the two governing equations. And of course, you can make this a lot more complex. You can have, if you have 3 phases, and usually you have 3 phases. If you have a unique design, then you have partial C, partial X, partial C, partial Y, partial C, partial Z, and you can derive this equation in 3 directions. Okay. So then when you think about, so now I have my 2 equations, and now we're gonna talk about that at steady state. And this is very important to remember this, is that at steady state, the rate of diffusion and the rate of reaction are equal, right? So this rate of diffusion is equal to this rate of reaction. And what I'm saying basically is that at steady state, these 2 guys will have the same value, right? So what this means as well is that at steady state, the amount of molecules reaching to the surface will always react, right? So if these 2 guys are equal, I'm gonna equate these 2 expressions right here. And this is what I did. KL CAL minus CAS is equal to KR CAS. So I'm equating the 2 expressions, and I'm gonna solve for CAS, which is the concentration on the catalyst surface. So if you rearrange and solve for it, you're gonna get this expression right here. And then if I plug this expression back into my reaction rate equation. So if I plug the expression I have back into here for CAS, and the idea is that I want to get an expression which combines both my reaction rate, my reaction, and my mass transfer. So I plug this back here and I rewrite it. I'm going to get this expression here. And this is very important and when you think about it. So my overall change in number of moles when I have a heterogeneous system that involves a mass transfer resistance and a reaction rate resistance is equal to minus AV CAL. And again, this is your surface area per unit volume, and this could be a function of the catalyst, could be a function of the liquid nature, whatever it is, multiplied by the liquid bulk. Okay, this is very important. This is your liquid or the gas bulk, right? Gas or liquid bulk. Bulk concentration divided by two resistances, 1 over KL for the mass transfer, 1 over KR for the reaction. And this format, you must have seen it in heat transfer, where, you know, if you want to calculate your overall heat transfer coefficient, it's a summation of 1 over maybe K dO plus 1 over H plus, you know, it's just a summation of 1 over a bunch of resistance, usually 1 over U, right? And the idea is very similar. Again, there's a thread along all the transport theories, all the transport physics, right? And what this represents basically is your driving force, your driving potential, which is AV multiplied by the bulk concentration, divided by the total resistance. And your total resistance will always be the summation of the inverse of your mass transfer resistance plus your, or mass transfer coefficient plus 1 over your reaction rate coefficient. And again, KL is your mass transfer coefficient, KR is your reaction rate coefficient. And this type of format is very common for multi-phase systems. And if you end up taking your PE exam, you know, if you work for a few years and you want to do your professional engineering exam, they like to test this type of idea a lot, where they tell you, oh, I have a gas liquid system, the reaction rate is this, the mass transfer coefficient is this, find the change in number of moles with time. So you just divide 1 over KL plus 1 over KR, and you plug it into this type of form, and you get your number, okay? Good. So now let's take a closer look at this equation and try to maybe analyze it a bit. So this is my overall change in number of moles, or this is the reaction rate based on unit volume, if you want to call it, is equal to your overall reaction rate per unit volume, or the overall change in number of moles per unit volume is equal to my driving force, which is the AV, which is the surface area per unit volume, multiplied by CAL. And again, we said CAL is the concentration in the bulk, right? Not CAS. We equated the CASs and we kicked them out of the equation. So now I only have the CAL, which is the concentration of liquid at the bulk, divided by my two resistances, 1 over KL, or 1 over my mass transfer coefficient, represents my mass transfer resistance, plus 1 over KR, 1 over my reaction rate coefficient, represents my reaction rate resistance, or my reaction resistance. If KL is much larger than KR, then the potential rate of mass transfer is fast compared to the reaction, and the reaction rate is dependent on KR alone. So if my mass transfer coefficient is much larger than my reaction rate coefficient, then most of the time you can just drop it out of the equation, and your overall process or your overall reaction rate is only a function of your reaction rate resistance, right? And this is called a reaction rate, a reaction controlled process, right? On the other hand, if KL is much smaller than KR, so if KL is much smaller than KR, then this expression controls or governs this, how fast your reaction is happening, and the potential rate of reaction is much faster compared than that of mass transfer. The reaction rate depends on KL alone, and CAS is very low, and it's called a diffusion limited reaction or a mass transfer limited reaction. Okay, so you have two ends. You have either reaction rate limited reaction, or a diffusion limited reaction, also called a mass transfer limited reaction. And depending on the nature of your process, you need to identify whether it's mass transfer limited or reaction limited, and then this will be the starting point to guide your practical design of the reactor, whether I want to have mixing, how important is mixing to the process, all of these details. And in a mass transfer limited reaction, the major slowing step will be how the molecule finds its way from the bulk phase all the way to the reaction surface. However, once it finds its way to the reaction surface, the reaction will happen very readily, will happen almost instantaneously. And in diffusion limited reactions, most of the time, the concentration at the surface is zero, right? And the idea here is that, let's go back a bit, because this process is so much slower than the reaction, then any molecule, once it hits the surface, is going to react and disappear immediately. So the concentration at the surface will be very low. Okay. And again, this is a similar analysis, and this is sort of a more complex analysis where I have a gas, liquid, solid system. So if I have a gas, liquid, solid system, and I'm reacting two gases on the surface of the solid, you think from the left-hand side here, this is my gaseous bulk, and the pure gaseous reactant A has to hit my gas-liquid interface, diffuse through the liquid film, then diffuse through the bulk liquid phase, and then diffuse through the solid film, basically. And then once it gets to the solid surface, it's gonna react, right? So now I have more resistances, right? So like unlike the previous case where I only had one mass transfer resistance, here I have three more mass transfer resistances. So I'm gonna have 1 over KL1 plus 1 over KL2 plus 1 over KL3, then plus 1 over KR for the reaction here. And now I have more resistances, and depending on the nature of the system, I need to compare which one of these resistances will really control the process. If you find out that, the main body of liquid, this mass transfer resistance here is so much lower, and it's actually controlling the process, and this is because the liquid is very viscous, then yeah, you can design your system so that maybe you're gonna add an additive to reduce the viscosity of your main body of liquid so that mass transfer is much higher. If you do it here and you find out that the biggest mass transfer resistance is at the gas, the biggest mass transfer resistance, i.e. the lowest mass transfer coefficient, is at the gas-liquid interface. And this is because, we're operating at a very high velocity and I'm only getting very huge bubbles with a very low surface area to volume ratio. So you can design your system now to maybe use a sparger or, a sieve sparger or a perforated plate, which can introduce much smaller bubbles. This way you have a much higher surface area to volume ratio, and a much higher surface area to volume ratio then translates to a better or reduces this resistance, and you can drive your process forward, okay? So once you start thinking about it in terms of the competing resistances, in terms of the mass transfer coefficients, it starts giving you a starting point for your design, or, for thinking about your reactor. And again, so this is the equation for it. So I have 1 over V dNA by dt, and this is the overall reaction rate, and it's a function of, in this case, he wrote it as 3 resistances, which is fine. I have 1 over Ka, which is the mass transfer coefficient for the gas-liquid film, 1 over Ka prime, which is the mass transfer coefficient for the liquid-solid film, and then 1 over Kr, which is the reaction rate coefficient. And the resistance which Levenspiel eliminated here is basically the resistance through the liquid bulk. And you can eliminate this resistance in many cases by assuming that, the gas and the liquid are in equilibrium. So I'm going to have a baseline equilibrium concentration here. And however, one thing to look out for is, in this case, the difference here, I don't have my my A parameter at the top. However, I have a specific A parameter for my gas liquid and my liquid solid, right? And this is important when you have 3 phases. You need to separate your interfacial area, or your surface area per unit volume, you need to separate it for each each pair of gas liquid and liquid solid. So in this case, I have my mass transfer coefficient for gas liquid, and I have my gas liquid interfacial area per unit volume. And this gas liquid interfacial area is basically depends on the bubble, your average bubble size. So you get your average bubble size, you calculate its area, you calculate its volume, you divide these two expressions, you get your interfacial area for the gas liquid interfacial area. Then moving on to the liquid solid film, this is my mass transfer coefficient, and I have liquid solid interfacial area, and this is different than the gas liquid interfacial area. The liquid solid interfacial area in this case depends on the size of the catalyst particle, right? So if your catalyst particle is very fine, this liquid solid interfacial area is very high, and if you're using a very fine catalyst, liquid solid interfacial area, or the surface area per volume ratio, will be very high, and you can see this resistance becomes low, right? If I have very big bubbles where my surface area per unit volume is very low, then this becomes a big resistance and slowing my process. So now you can take it, put it into context, and you can see how they behave within your system. And then Kr is your reaction rate coefficient, and again the minus CAI is the interfacial, or is the concentration in the bulk. It's not the concentration at the surface. And in all of them, where the general idea in this is that your rate per unit volume is equal to your driving potential divided by your total resistance. And this is really the governing idea, or the governing physics behind a lot of the chemical engineering ideas. Okay, and this is very similar, talking about chemical engineering ideas and physics and all this stuff. You can see it here in heat transfer. Hopefully you've seen this before in heat transfer. However, if I want to transfer heat from a hot fluid to a cold fluid separated by a solid wall, very similar idea. Hot fluid, I have my hot temperature. This is the temperature of the wall on the outside. This temperature of the wall on the inside. And this is my cold bulk temperature. My overall heat, or my overall Q, is equal to minus UA T hot minus T cold minus A T hot minus T cold. And again, this is similar to having your interfacial area, and your overall heat transfer coefficient, or your overall resistance, is a function of the elements forming it, right? So I have 1 over HI, which is the resistance here, XW over KW, the resistance here, 1 over HO, H naught, the resistance here, or H out is the resistance here, right? And these are, these depend, this is maybe your, these factors, this factor depends on the nature of the solid wall. This factor depends on the properties of the fluid here. This factor depends on the properties of the fluid here, all right? Very similar idea. Okay, let's move on. And this, we've talked about this last week, but it's good to just remind you that if you want to play around with the mass transfer, or ways to overcome mass transfer resistances, or that's the reason there exists different operating modes, such as co-current, counter current, cross current, having a continuous phase or having a discrete phase. A discrete phase basically means having bubbles, drops, or particles. So if I'm bubbling gas in a liquid, my gas is called my discrete phase. My liquid is my continuous phase. If I'm fluidizing catalyst particles, in a gas phase, where basically I push these catalyst particles and make them dance in an upstream of gas, then my solid is my discrete phase, and my gas is my continuous phase. And understanding which is the continuous phase and which is the discrete phase has some benefits if you become a technologist for a specific piece of equipment, where you need to do fluid dynamics modeling, or you need to do some specific modeling, okay? And these flow patterns help you minimize these resistances. The whole idea of having a flow pattern, or having a mixer or any other type of configuration, is to minimize these resistances at the scale you want to operate to make the reaction happen readily. Okay, so this is the end of chapter of the heterogeneous system discussion. And again, this is the second last two parts of Levenspiel. You can always have a look at them. The book is posted on Blackboard. You can always have a look there and browse through it, see the different ideas presented. Okay, so now I'm gonna provide you, or let's talk a bit about the final exam and just a quick review about the different ideas we talked about this semester. And again, your exam will be comprehensive, so expect either a problem from every sort of idea, or maybe a problem combining multiple ideas, A, B, C, D, taking you through them, right? Again, we started off by talking about the rate of reaction, how to define the rate of reaction, whether it's based on the unit of volume of a reacting fluid, based off unit of mass of solid in the fluid solid system, interfacial area. You can see that I can write the rate of reaction as in many forms, right? And then for an nth order reaction rate constant, this is how you get the units. So just make sure you know this. When it was on the first test, it's a very easy thing to get, and just maybe practice it a bit, a couple of times to make sure you don't drop these easy points. But yeah, for an nth order reaction, this is how you get the units for the rate constant. Molecularity, order of reaction, you should know all of this stuff. Temperature dependence on the rate equation, again, this is Arrhenius type format expression, and we've talked about this where your temperature, your reaction rate constant, your reaction rate equilibrium constant, your thermodynamic equilibrium constant, they all follow this type of Arrhenius relationship to get them at different temperatures. Okay, and then we have this example. Okay, you should be able to know it. And then we have our cases. At the very beginning, we talked about different cases for different classes of reactions and introducing the idea of a performance equation, all of this stuff. So case one, we said, is for an irreversible unimolecular first order reaction. A goes to products. This is your reaction rate expression. Minus RA is KCA. You take an integral, you get this expression. So for a first order reaction, you can always use this expression to get the concentration as a function of time. You can actually plot it as a function of time. And this would be your performance equation. And again, and we're talking about this within the context of interpreting ideal batch data reactor, right? So if I give you a bunch of points, I told you, I measured this in a lab for this reaction, find out what the order of this reaction is. You're going to test this experimental data against the expressions for the different cases, and whichever expression fits is the order of your reaction, right? And then we introduced the idea of fractional conversion. Hopefully now you're all comfortable with conversion. If you don't know what conversion is, you're in trouble. But basically, conversion is defined as 1 minus Ca over Ca naught. It's the amount of species which reacted, basically. So if I tell you I have 10 moles and the conversion is 0.4, that means that 4 moles reacted and I have 6 moles left. If I tell you I have 100 moles and conversion is 90%, that means that 90 moles reacted and I have 10 moles unreacted, right? Then basically you can always rewrite any expression of concentration in terms of conversion. One point I want to make here is there's a couple of you, or actually a chunk of you, who tend to convert everything to conversion when solving a problem. That is fine. However, just be aware that sometimes converting your equations from concentration to conversion might make the math a bit more complex. So it's always good to sort of be comfortable solving your problem both ways, and with practice you're going to recognize when to go ahead with the concentration expression, when to go ahead with the conversion expression. Okay, this slide, not sure what's going on with this slide, but anyways, I'm gonna fix it when it's uploaded. So for a case one, we have a reversible unimolecular order reaction. That's what it's going to look like. Okay, then case two, you have an irreversible bimolecular second order reaction. In this case, I have A plus B reacting to give me a certain product. And again, you should also understand the idea of elementary and non-elementary reaction. An elementary reaction is one which follows the stoichiometry. So A plus B goes to products and the reaction rate expression is equal to K, Ca, Cb. This is elementary because this matches the reaction or the stoichiometry here. If for some reason this is K, Ca to the half, Cb to the 0.4, this is non-elementary, right? Because it does not match. And again, we talked about this, and this is, you just, you go through the different derivations, and I have my final expression where I have ln m minus xa over m of 1 minus xa is equal to kca naught m minus 1, and this is equal to this expression here. And again, m, we said, is the ratio of your two reactions, and it was introduced sort of make the math easier, right? So in this case, m is equal to Cb naught divided by Ca naught. Okay, and this expression is not valid for m equals to 1. So, if you have an equimolar starting mixture, you should be aware that I need to use a different expression, right? And this idea is important because, just be aware of this idea when solving problems or if you get faced with this type of problem. Okay, and then I have case 3, which is irreversible monomolecular second order reaction, which is basically this equation right here, right? It's irreversible monomolecular second order. So in this case, I have 2A goes to products. My reaction rate R is equal to K Ca squared. Okay, case 4, we talked about empirical rate equation where I have an nth order reaction. And again, for an nth order reaction, this is your expression for n equals 1. You have to look at case number 1, right? Where, if n equals 1, it's just the first order reaction. Look at the first order reaction. For n equals 2, you can always look at the second order reaction. However, this equation is also valid for second order reactions or for n equals 1. And we did some trial and error. We had, I think, a couple problems where we went through a trial and error process to get the reaction rate. Okay, for a zero order reaction, this is my expression right here. Ca is equal to Ca naught minus Kt. And we also talked about the idea of Tmax. There was one of the problems where we talked about Tmax as well. Okay, the idea of reaction half-life. Half-life should be basically the time it takes for half the chemical to react or to disappear. Then we talked about, ideal batch reactor, plug flow reactor, CSTR. Hopefully you guys are comfortable with these three. Basically, a batch reactor is a non-continuous system where you have a mixer mixed with, okay, sorry about that. So you have your ideal batch reactor here, you have your plug flow reactor, and then you have your continuous stirred tank reactor. And hopefully, by now, we've talked about these guys a lot, and we know the differences between them. But so your ideal batch reactor is a non-continuous system, and I've noticed maybe in the last exam there's a bit of confusion between the batch reactor and the continuous stirred tank reactor. A batch reactor is non-continuous. I just put in the fluid, I mix them, or I heat them, or whatever, wait for the reaction to happen, and then take the products out. It's like cooking, right? You put all your ingredients, you cook them for a bit, and then you have your product there, ready to sell or to serve or whatever. A plug flow reactor and a CSTR are both continuous systems, right? And by continuous systems, it means that the reaction is happening along with the flow, right? So the feed enters this reactor, you might have a catalyst, you might have some other arrangement in there, and then it reacts while it's passing through and I get the product. And the CSTR feed enters my basically fluid basin, I have a mixin, and then I get the product, okay? These two continuous, this guy non-continuous. Okay, and these are the differences. Make sure you know them. This might show up on a multiple choice sort of This might show up on a multiple choice part of your exam, your ideal batch reactor, plug flow reactor. CSTR, just understand different nature, the nature of the different elements. Okay, I'm not sure what's happening here. I'm gonna fix this slide. But basically when deriving your equations, your ideal batch reactor is isothermal, constant density, and this is the performance equation for the ideal batch reactor. One thing to remember about the ideal batch reactor as opposed to your CSTR or your PFR, your ideal batch reactor, we have the time variable, whereas for a CSTR and a PFR, the equivalent of this time is your space-time, okay? So just understand the idea of space-time, how it behaves the same way or does the same job as time does in a batch reactor, okay? This is your IBR performance equation. Again, your CSTR, I'm gonna fix this once we upload it. I'm not sure why is PowerPoint acting up, but that's fine. So, and then we introduce the idea of space-time, and that space-time is the time to process one reactor volume of feed. Okay, and then you have the space velocity. I haven't really talked a lot about space velocity, but space velocity is 1 over space-time. All right, then you have your CSTR performance equation, V over FA naught, tau over CA naught is equal to XA over minus RA. We've used this equation, probably the equation we use the most throughout this course. So make sure you know how to deal with it and how to use it. Again, a plug flow reactor. And then we said the thing in a plug flow reactor is that the elements don't mix in the axial direction, right? So as your fluid is flowing along the path of the reactor, this element right here is not going to mix with this element, is not going to mix with this element. And this is the ideal nature of this unit. And the PFR performance equation, as we said, V over FA naught, tau over CA naught, this is basically a unit conversion right here, is equal to integral minus 1 over CA naught, CAA, from initial to final dCA over minus RA. Okay, then we had a discussion about why are the equations for the IBR and a PFR so similar. And just be aware of this conversation, of this discussion. Okay. We then moved on to talk about size comparisons for single reactors, how to know these different ideas of, comparing a PFR to a CSTR and how a PFR will always do the same job as a CSTR, however, in a much smaller volume. And if we compare the volume of a CSTR to the volume of a PFR, you'll always find that volume of a CSTR is always larger. It starts at 1, right? And then just keeps on increasing. So PFR can always do the same job as a CSTR with a smaller volume. This is the idea I'm trying to convey here. And then we talked about having number of CSTRs in series and how, having number of CSTRs in series there now. The more CSTRs in series you have, the closer you get to a PFR performance. As well as, if you want to scale up the process to achieve the same conversion, right here, it's always better off to break your CSTRs to smaller number of CSTRs than to just increase the volume of a CSTR, right? Let's go back and just revisit this figure. So this line right here represents this represents 1 CSTR, and I'm increasing the volume of the CSTR, right? So as I move to the left or as I move upwards along this line, I'm increasing the volume of the CSTR. And the idea here is that if you want to achieve a higher conversion, so if I want to move to the left of my x-axis to increase my conversion, instead of using a larger CSTR, you're always better off using a bunch of CSTRs in series, right? So instead of going along this line this way, I'm always better off going along this blue line this way by just putting or dividing this CSTR into a bunch of smaller CSTRs. And as you can see here, the more CSTRs I have in series, the closer I get to the PFR performance. So as n approaches infinity, I get closer to the V, the V ratios to be equal to 1. So I'm approaching the PFR performance. Okay. So this is the take-home points. Just make sure you understand them, make sure you remember them, etc. Then we talked about equal size CSTRs in series. You know, equal size CSTRs in series will start behaving like a PFR. And if you derive your reaction or if you derive your equation, you can always cancel out these expressions to get this expression, which then you can use in conjunction with this expression right here to solve a problem where you're comparing CSTRs in series to a single PFR. Talked about multiple reactor systems, plug flow reactor in series, and how, you know, how they behave, whether they're in series, whether they're in parallel. Please read this. The recycle reactor as well. We talked about the recycle reactor and how it behaves. So just make sure you read this. And then we started to move on to different ideas where we started talking about series reactions and parallel reactions, okay? And a system of reactions in series, or we started off with the parallel reactions, right? So let's talk about the parallel reactions where I have A going to R and A going to S, and I only want one branch of this parallel reaction system to occur, and I want to slow down the other one. So, you know, you want to maximize your desired product, however, at the same time, you want to minimize your reactor size, you want to minimize your reactor complexity, and other pertinent details of your system. And then we said the approach to do this is we're going to use concentration instead of conversion, and we're going to eliminate the time variable. And the idea here is I'm dividing the reaction rates of both reactions and seeing the governing concentrations, which can derive which reaction forward. So in this case, I have A goes to R, A goes to S. These are my reaction rate expressions. I divide my R for the desirable reaction divided by the R for the undesirable reaction. I get an expression which is usually a concentration of my reactant to the power of, you know, the orders, summation of the orders, or difference of the orders in this case. And you can, you know, and we talked about, and this was very recent, just last exam, where we talked about, you know, how you can use this to decide what type of reactor you want, what type of mixing you want, and using the activation energy to determine whether you want to operate at a high temperature or a low temperature. So if the activation energy of your desirable reaction is higher than the activation energy of the undesirable reaction, you want to operate at a high temperature. If the activation energy of your desirable reaction is lower than the activation energy of the undesirable reaction, you operate at a low temperature. Okay. We then talked about the three cases where A1 is greater than A2, operate in a batch of plug flow. A1 is less than A2, you operate in a PF or CSTR. A1 equals A2 has no effect. However, you should use a PFR to reduce your reactor size. Okay, and then you have this unique case where everything is equal, then, you know, it doesn't matter. You can just put the two chemicals in touch and they'll react, right? And then we talked about the contacting patterns. So if I can have both concentration. Sorry, so if I have a system of A plus B going to R and a system of A plus B going to S, again, this system is in parallel, right? And if I write my reaction rate expressions, I have R is equal to K1, CA A1, CB B1, RS is equal to K2, CA A2, CB B2. I have my first contacting pattern. So if I need both my concentrations to be high, if A and B, I just drop them all at the same time. And these images are for a non-continuous system or a batch system, right? If I need both of them low, I slowly introduce them into a batch of inert. If I need one of them high, then I have my batch reactor filled with one of the chemicals, and then I slowly introduce the second chemical. Okay, so on the other hand, these are for non-continuous systems. So for a continuous system, which is basically a CSTR or a PFR, in this case, I have A1 greater than A2, B1 greater than B2, and I want to keep both my species, the concentration of both of them high. So in this case, I just introduce them both at the beginning of my PFR at a very high rate. If I want to keep them both low, I introduce them both at slow flow rates into a CSTR, maybe filled with an inert, or just introduce them slowly into a CSTR, or you don't want to introduce them slowly in a PFR because PFRs are usually pressurized vessels, and you don't want to have vacuum, or you always want to keep the flow matching the pressure. You can always pressurize this with an inert, however, separating gases is more complex than separating liquids. Anyways, but these are ideas for later on. If you want to keep one of them high and one of them low, we can always introduce one at a high concentration initially, and then slowly introduce the other at different ports of the reactor. You can do it in a PFR in this sort of arrangement, or you can do it in a CSTR in this type of arrangement. And then we talked about the idea of instantaneous fractional yield and overall fractional yield. And you had a problem on your test on how to deal or how to use the idea of an overall fractional yield to determine the concentration of the desired product in a parallel system. And this is important because you cannot just use a CSTR performance equation to do this, right? The idea is that you have two reactions happening at the same time, and you need to separate the two ideas, and you need to solve your performance equation with the product you want in mind. Okay, so we said for a PFR, you get your fractional yield is just 1 over delta CA integral of the instantaneous fractional yield dCA, and the instantaneous fractional yield is the moles of the product you want divided by the overall, or moles of reactant, right? For a CSTR, this is your overall fractional yield, and to get the exit concentration of R, you multiply your overall fractional yield by the change in concentration. So if I want to get the exit concentration of R for a PFR, I multiply this expression by this, I just plug this expression here, and I get the exit concentration of a PFR. If I want to do it for a CSTR, I take this expression, put it here, and I have my expression for a CSTR, and I can use it to calculate my exit concentration of the species. Okay, and then, this was a big part of your second exam, and you should expect to see, maybe a couple of multiple choice ones on the final. What choices should we make in terms of temperature, concentration, batch, semi-batch, continuous, all of this stuff? If I have A plus B going to C and D, system, parallel system, and there is no effective concentration, however, E1 is greater than E2, you want to operate at high T, and at the same time, you want to operate at high concentrations, okay? On the second test, I allowed you to pick, since there is no dependence on the concentration, if you picked any type of system, I said it's okay. However, in reality, you want to take the volume of the reactor in mind. So you want to keep the concentrations high to keep your reactor volume low. And in this case, we operate in a PFR. Similarly, just along the same lines, you want to keep CA high and keep the temperature low. All of these ideas we've talked about them. You can revise them on your own time. We then started talking about series reactions and systems which are series with respect to one species and parallel with respect to the other. In the governing principle, when I have systems which are complex, right, or systems, again, and this also applies for systems in series, is that I don't want to mix elements of fluid with different compositions, right? So you don't want to have a recycle. You don't want to, introduce a fresh feed halfway through the reactor. You always want to minimize mixing of fluid elements at different compositions, at different conversions, okay? And this governing principle is very important. You go read the slides, you had a couple of examples there, and try to understand the basis for this principle and how it came out, how it came. Okay, and then we have these equations for quantitative analysis for plug flow or batch reactor, where you can calculate the maximum concentration of the intermediate and you can calculate the optimum operating space-time. Similarly, so this equation is for a batch reactor or PFR. This is the same equation here. This equation determines the maximum concentration of the intermediate. Equation determines the time at which this maximum concentration happens. And we said in some cases these equations fail, right? So if I take a look at my equations here, just 1 second. Okay, if I take a look at these equations here, if for some reason K2 and K1 are the same, then I'm gonna get, I'm gonna get a 0 in the denominator here. It doesn't make sense. I'm gonna get a 0 in the denominator here. It's just the math will fail, right? This equation will fail at these limits. So in these cases, when the equations fail, you can always look them up in the chart. You can always get the value from the charts here. Similarly, for a CSTR, these are the equations to get the maximum intermediate, the time at which you have the maximum intermediate. And this is the equation to get the value of the maximum intermediate. Now, the equations for the CSTR will never fail because, unless one of them is 0, and if it's 0, then you don't have a series reaction, right? But K1 multiplied by K2, K2 over K1, these equations won't fail, so you can always use them to determine your values, or if you want, you can always use the charts. You're going to get the same answer. And then we talked about the idea of, the PFR will always give you a higher yield than a CSTR. So a PFR will always give you a higher yield in a smaller volume than a CSTR. So PFRs are, so I have a lot of PFRs in industry, especially in petrochemical industries. You'll never see a CSTR. CSTRs, you see them sometimes in pharmaceutical industries. The advantage of a CSTR is that you can have better control on the system, right? That's why you see them in critical systems like pharmaceuticals, where you really want to control the concentration. And other, chemical sort of specialty chemicals, you see CSTRs a lot, making lubricants for cars, or, companies that make lubricants, that make additives, where you really need to have a very fine control of your concentrations, of the nature of the chemical, of the rate of polymerization, etc. Whereas in oil and gas, for example, is just pumping product all the time. You operate within margins which are somewhat loose in terms of product quality, then you always have PFRs operating alongside distillation columns, right? Okay. And then we have some specific cases. We didn't go through them in details. However, it's good to know them as you exit this course. Just read them again, keep them in mind. Two-step irreversible series parallel reaction as well. Please read this. And again, the governing equation, where we don't want to mix species at different levels of conversion, also applies here. And these are the conclusions. Just read them at your own time. Okay. We then talked about temperature and pressure effects, specifically the effect of temperature on an equilibrium system. And again, equilibrium system is not an irreversible system. An equilibrium system is a reversible type. Most of the time, it is a reversible process, and you want to find your position in the equilibrium, right? And you need to understand that equilibrium, the idea of equilibrium is different than the idea of steady and unsteady state, right? You can have a system which is at steady state, but not in equilibrium, right? You can have a system which is unsteady state, however, it is in equilibrium, okay? Different ideas, make sure you dissociate them from each other and make sure you think about this a bit. And we talked about, when thermodynamic equilibrium constant is very high, it approaches an irreversible reaction. The thermodynamic constant is very low. It's only like can only have low conversions, okay? And these are your equilibrium lines. And we solved this problem where you're given Gibbs free energy, you're given an enthalpy, and you are being asked to determine the operating temperature range, okay? And this idea again is very important, where first of all I use my equation where delta G is ln K over RT, or minus ln K RT, or minus RT ln K is the easiest way to remember it, or K is equal to exponential of minus delta G over RT. You get your thermodynamic equilibrium constant at a reference value, and then you can get it as a function of temperature. You can also translate it into conversion. Then you have two expressions, one for the conversion as a function of your thermodynamic equilibrium constant. Second is of your thermodynamic equilibrium constant as a function of temperature. Then I can use these two equations to get the temperature that will give me, or the conversion at every temperature, and you can use this to guide your design. And one thing I've noticed, if you get a temperature that's very low, then your calculations are wrong, okay? Things you need to know. If you get a temperature that's 240 Kelvin, which is very low, then your calculations are 240 Kelvin is minus 30 Celsius. If you get a number that's that does not make sense, then revise your calculations. Make sure you plug in the numbers in the calculator correctly. On the exam, you'll never get a problem that violates basic, basic thermodynamics or basic just, it's not going to violate your intuition. Okay, so use this to gauge what you're doing. If you get negative concentrations, make sure you have a calculation error somewhere. The concentration of the reactant is increasing throughout the system, something's wrong. Concentration of the product is decreasing throughout the system, something's wrong. You got temperature that's very low, something's wrong. Just revise your calculations. Maybe plug them again into the calculator and see if the numbers make sense. Okay. The idea is just read the slides, make sure you know this, and then we talked about the operating line and how to use the XA versus -1 over RA chart to sort of guide your design or look at your operating lines. And we talked the idea of isothermal, non-isothermal, exothermic, all this stuff. Just read these at your own time. And we introduced equations, conversion as a function of heat capacity, as a function of enthalpy. Just know them. And then you have also talked about this equation where you can operate adiabatically, you can operate adiabatic exothermic, adiabatic endothermic, decrease in inerts, increase in inerts, all of this stuff. And again, understand the idea of having an adiabatic system, exothermic system, endothermic system, because even though if you go work as a process engineer, you might never get exposed to, you might never hear the word adiabatic again, right, in your life after you graduate. However, it governs a lot of the basic principles of design. So even though on the ground, you might never hear it. However, if you end up progressing through your career and you have an interest in staying on the technical side of engineering, of process engineering, it's good to have a basic understanding of these concepts because they govern a lot of the basic principles that that also govern a lot of the things you do on the ground. Okay. However, if you want to move on to management or something else, you're fine. No, just study it. Okay. XA versus T, you have your enthalpy again. You can always, if I add heat to my system, I can shift my system away from adiabatic conditions and I can move it towards isothermal conditions. You can basically operate or rotate the operating line using heat transfer equipment. Okay. And then we talked about different configurations for exothermic systems, for endothermic systems. In this case, I'm using the exothermicity of the reaction to heat up a cold feed so that I also cool my product. So I have a cold feed coming. It's being heated up by the exothermicity or the heat released from the reaction so that by the time it arrives at the inlet of the reactor, it's hot. And at the same time, it cools the product so that the product is at a reasonable temperature. Alternatively, you can have interheaters where you can, divide your system into different smaller blocks and have a heating element or a heater between every reactor. Similarly, for endothermic, we have a similar idea. We use a furnace and to just heat up your feed to the temperature you want before the reaction. And these are different configurations. And then last week, we talked about the rules for reactions, minimize the reactor volume, keep the concentration as high as possible for as long as possible. If the reaction is order is greater than 1. So try to read these rules and try to relate them to what we learned and relate them to what's going on. Continuous, non-continuous, we talked about all of this stuff. And then when we were talking about the ideal scenarios and the effect of flow, we said there are 3 main factors, right? Somewhat interrelated. First one is the residence time distribution. Second one is state of aggregation. Third one is how early you mix your streams. So when it comes to residence time distribution, basically how long does your fluid live or exist within the reactor? And residence time distribution can give you an idea on presence of stagnant regions. For example, in a baffled reactor, you usually have stagnant regions in the corner. And if it's a packed bed or if you have catalyst here or if, those are just area which is underutilized, right? Similarly for a CSTR, maybe the mixer is running too quickly or the blades of the mixer are too large or too wide. So it just, you introduce the fluid from the top, it never gets to the bottom, you never have mixing here, and just being, everything is happening at the top of the reactor. And we talked about these different scenarios. You can listen to the previous slide. State of aggregation, we then talked about macrofluids, microfluids, and how you might have aggregations, how you might have bubbles coalescing, all of ththese ideas. Earliness of mixing as well, how early do you want to mix? Do you want to mix towards the end of the reactor, the beginning of the reactor? Do you just want to use the momentum of your fluid to make some mixing and then induce some mixing with an impeller later on? All of these ideas affect your actual patterns of reaction. And depending on which one of these parameters is the governing principle, you use it as the basis for your design of your reactor. And then this wasn't the last homework, and this will definitely come on your on your final. The idea of having a tracer, right? This wasn't the last homework, and it's the only homework between really the. Is it the only homework? I think it is between exam 2 and your final. Maybe there was another one. It doesn't matter. This is going to show up on your finals, so make sure you know how to do it. We have a continuous system, and I introduce a tracer. At the beginning, a tracer is introduced using a direct delta function, basically an impulse. So as you see here, I just drop a tracer, and then I measure how, or its concentration as it exits the reactor. And this will give you an idea on the flow pattern, on how long it takes to stay in the system, all of these ideas. And in the homework, we discussed how you can basically do a mass balance by just looking at the surface areas under the curves. And I told you to read the examples in Levenspiel, so make sure you read them, make sure you're comfortable with this. We'll go over it next week as well when we're solving problems for this problem. Okay. Then we had an example which system would give a higher conversion, system 1, system 2. We look at the RTD versus time, and you basically do a mass balance to determine which system is operating efficiently, which is not, okay? So this is the end of the review slides. In addition to the slides we talked about today, please read them and prepare for next week. Next week we'll just start solving problems and preparation for the final. The review set for the final, I'll either put it online today or tomorrow morning. It will probably be about maybe 20 questions or maybe 15 to 20 questions, a long set. It will take you time to absorb. However, if you're comfortable with all the questions and how to solve them, you should be good to go for the final, and you should be ready for the final. And then you have a couple of weeks to really read and prepare. So take your time, read it, come back with questions, and then let's talk. Make sure you're ready and comfortable before the final. Okay, thank you very much. I'll talk to you guys next week.